Howdy. The purpose of this video is to talk about thermal expansion. We're going to describe both the macroscopic description of thermal expansion, and we're going to think about what happens on an atomic level. Now, why do we care about thermal expansion? Well, if we don't engineer our materials properly, we could see something like this. This is a railroad track that has buckled. So as it heated up, perhaps seasonally, the railroad ties would tend to expand, but there's no place for them to expand linearly. And so what we see is this buckling behavior. So because of this, we have to take into account the way real materials interact with temperature changes. You might be familiar with seeing something like this on a bridge. This is called a thermal expansion joint. And these are designed exactly so that the bridge doesn't buckle like that, because if that bridge buckles, it's going to fail. So what we do is we take into account how much we would expect the bridge to expand at its highest temperature, and we give it some wiggle room. We allow it room to expand. Now, what we're going to talk about here is how materials behave with changes in temperature. So first, let's think about a macroscopic description. And to describe this expansion with temperature, I can define what's called the coefficient of linear thermal expansion. So that's this term alpha sub L. It's defined as 1 over the length times the change in length per unit temperature. So for every degree Celsius, Kelvin, Fahrenheit that the material heats up, there will be some change in length. So that term is defined as dL dt. Now let's think about units of the coefficient of linear thermal expansion very briefly. If I have dL over L, those are both in units of length, so they'll cancel out. So the units of this are given in 1 over Kelvin, 1 over Celsius, 1 over some sort of temperature unit. Another thing is that we see right off the bat a dL over L term. So let's think back to something else that looks like that. Let's think back to a strain, right? Strain is elongation over total length. If we're talking about engineering strain, that's the original length of some material. So I could define a thermal strain in here as well. So another way to rearrange this expression would be to say alpha dt equals some thermal strain, right? If the linear coefficient of thermal expansion is relatively constant over some temperature range, then I could replace dt with a macroscopic change in temperature difference, right? So alpha delta T equals thermal strain. Okay, so why is this important? Well, let's think about some part, and I'm going to have that part confined. So here's some sort of top barrier and bottom barrier, and here's the part. Now if I heat this part up, it's going to want to expand, and the expansion that it would want to see is given by this expression here, right? So let's think about if this bottom barrier wasn't here. If it heats up, it's going to want to expand, and really I'm only thinking about this expansion in the one direction, so the linear coefficient of thermal expansion. However, we know that this barrier is here, so what happens is that the barrier is supplying a force and ultimately a stress back on this component. I'm pushing back on the component in the opposite direction so that it retains its original length. And so the way we would figure that out is we would look at a stress-strain curve and say what sort of stress is needed to apply to counteract that thermal strain, right? Because the two strains have to be equal if there's no net change in length. So this is why we care about thermal expansion. So there's also a volumetric definition, because if it's expanding in all directions, there would be an overall volume change. So you can occasionally see a volumetric coefficient of thermal expansion, and that's defined very similarly. Now, where does thermal expansion come from on the atomic level? You'll remember that we talked about bonding curves before, right? And this is looking at the bond between two atoms, and we're plotting the energy versus the interatomic distance, so versus the distance between those two atoms. So we said before that at 0 Kelvin, um, the equilibrium distance is going to be given by that energy minimum, right? So I would call this R naught. R naught. That's the equilibrium distance. So that's if there's no temperature in the system. But what happens as the system starts to heat up? As I heat up the system, I'm giving it more kinetic energy. So now I'm able to access slightly higher energy levels between those two atoms. So in other words, if I heat it up, the atoms are able to start vibrating to some extent so that the total energy can be a little bit higher than it was before. So let's say I give it some thermal energy that's equivalent to that, this small quantity. So now the atoms are able to vibrate back and forth between these two positions. And so I could consider what is the average position of those two atoms. And if I say that they're equally likely to access any of these states in between, then that average is going to bisect the distance between these 2 points. Let's heat it up some more, right? At this point, now I can access an even wider interatomic distance. The more thermal energy I'm putting in, the larger I'm able to get these vibrations to swing. So at this point, the average interatomic distance would be somewhere over here. And if we keep doing this process again and again, what you'll start to see is that the equilibrium thermal distance is getting longer and longer. And this is exactly what causes real materials to heat up, right? As I heat it up, this curve is always asymmetric. If I had a perfectly symmetric bonding curve, then I wouldn't expect materials to heat up. But by virtue of the fact that there's a finite distance that they can come together and they could go infinitely far apart, it is an asymmetric curve. Okay, so let's think about another thing. Let's compare two materials. One has a relatively strong bond, and so strong bonds are given by relatively large energy wells, right? So the other bond will be relatively weak. So one example would be something like a diamond or a tungsten, something that has it's a very refractory material, really high melting point. Something with a weak bond would maybe be the van der Waals bonding in between polymer chains. Now, if we do this same procedure, if we heat the material up in both cases, we'll start to see something pretty interesting. And that is that for a smaller amount of heating, we tend to get a larger change in equilibrium distance in the weaker bond than we do in the stronger bond. So again, this is the weaker bond, this is the stronger bond, and you see the slope here. The slope here is basically telling us what is the change in equilibrium distance per change in energy, but we could relate that back to a change in temperature, right? Because we're heating it up. So what this shows us is that the weaker the bond, the higher the thermal expansion is. And you can verify this. If you look at tables of thermal expansion coefficients, you'll see things like steels have a fairly small thermal expansion coefficient. Things like polymers and engineering plastics, they have a fairly large coefficient of thermal expansion. Okay, in review, thermal expansion leads to a strain, a thermal strain. If a piece is confined, that could create a stress on the piece, and that could ultimately lead the piece to fail, or it could lead it to buckle, like that image of the railroad ties we saw at the beginning. Thermal expansion ultimately is going to derive from this interatomic bonding, right? That's the atomic origin of the thermal expansion coefficient. And finally, the thermal expansion coefficient is going to be greater for weaker bonds. So the weaker the bond, typically the larger the expansion I would expect to see resulting from a small change in temperature.